Today, we're going to discuss how to use Monte Carlo simulation in AIMMS with the functions, programming languages, and the UI capabilities provided by AIMMS. We will first have introduction on analytical method to handle uncertainty. Then we'll take an example to show how to adjust AIMMS model to run Monte Carlo simulation. In the end, we will show a demo to run multiple simulations in parallel on AIMMS Pro. We're using this not rigid classification of analytical models as reference to understand uncertainties and decision making. So in this quadrant, we see there are two areas of studies, which is decision generation versus decision evaluation, and uncertainty and uncertainty circumstance. So optimization or mathematical programming in general, including linear programming, network models, integer and mixed integer programming, nonlinear programming, control theory, etc., falls to the strategy generation under certainty quadrant. The assumption here is that the input is known, also the relation between input and output is known. So it's worthy to point out that in the situation where input is unknown, forecasting is usually to get estimation for input. For example, demand, time required to finish project, or production yield, etc. And in other cases where the relation between input and output, or the relation between output and output is unknown, regression analysis could be the approach to get estimation for the relationships. And in the quadrant of strategy generation under uncertainty, there are different approaches for different problem and under different circumstances too. In the optimization space, we see stochastic programming and robust optimization are here. So stochastic programming handles uncertainty by associate inputs with probabilities and generate a decision to optimize the expected objective. And on the other hand, the robust optimization generate decision valid for all scenarios. So if you are interested in knowing more, my colleague Video Listis has a webinar available on AIMMS website talking about stochastic programming. Now, for this webinar, we're going to focus on how to evaluate the decision for under uncertainty. So we're going to use Monte Carlo simulation for that. So Monte Carlo simulation is a method for exploring the sensitivity of the decisions by varying input parameters to produce hundreds or thousands possible outcomes within the probability distribution and to evaluate the decision performance under those distributions. So the steps are usually we first have our decision generated by either LP, MIP, stochastic programming in the first phase. And then after that, we will first generate samples of uncertain input parameters from the probability distribution, and then we'll compute the decision outcome under the samples. And then for the decision we're making here, there may include both fixed decision and adjustable decision. For the fixed decision, what we mean here can also call it first stage decision, which means they cannot be changed regardless of the sample input of the parameters. So once the decision is made, it's fixed. And for the adjustable decision, or sometimes we call recourse decision, those decisions can be modified according to the sample input. So they provide more flexibility in the terms of decision making. So you can more call wait and see decision after the realization of the uncertain input parameters. So after we made the decision, adjust our decisions and created a new objective under the uncertainty sample, the next step is to evaluate the different outcomes occurring So the outcome can be either we want to see evaluate either the outcome meets certain requirements. So for example, if we're in an inventory and a production optimization model, we're trying to make evaluate how our inventory and production policy, whether it can meet our service level, or for example, 99% can meet all the customers' need. Or in the space of, for example, product design, we will see those parameters will determine whether it can meet the specification, for example, only 0.01% of defect rate. So that's one thing can be done to analyze the result. So another type of analysis is to get some statistical results. So for example, we want to understand the mean, the standard deviation, and our confidence level of the decision we're making under uncertainty. So after analyzing results, the last step is to visualize the results. So we will show that AIMMS WebUI in this case. So so for this webinar, we're going to show how we do Monte Carlo simulation through an example. So the example is in project planning. So this user, they want to make a set of strategic decisions to invest the company's assets and resources to maximize the economic value return. So they have various investment opportunities. So in this multi-year planning interval, for the investment opportunity, or we call a project, has the flexibility in start date, and moreover also has flexibility for the timing for the quantity of the investment and or divestment in other cases for assets. Also, we want to consider some budget and operational restrictions. So the model initially is formulated as a deterministic model. It's a mixed integer programming. So we want to maximize our objective, the NPV, net present value, under the certain variables and constraints, and then has AIMMS run optimization to get the solution. However, now we want to study, we will consider the uncertainty in some of the input parameters. So for example, commodity pricing, capital expense, operating cost, and different NPV discount factor, interest rate, for example, how our decision going to perform during if we consider uncertainty. And so that's the first question the user want to get answer. So the second question is, if we make a different initial solution, how will different initial solution, how are those various possible decision plans perform under uncertainty? So we're gonna try to answer those two questions by running Monte Carlo simulation in AIMMS. So the first step is to generate the sample. So first we want to declare a sample set, how many samples we want to generate. So what we're doing is we insert a set in AIMMS, give a name, get the subset under integers. So and then we generate from 1 up to number of trials, number of samples. So in this case, the number of trials will take a value 1,000. So we're going to generate 1,000 trials for each uncertain parameter. And then we're going to extend the uncertain parameter to the sample space. So one of the uncertain parameter we'll consider here is a expected commodity price. So that's we have originally have the price over, for example, over different location L. It's just one value for different location. And now we want to have each location have a 1,000 sample price. So we extend this parameter, we call it a sample price for each location and for each sample SF. And then after this, we're going to actually generate the sample data. So how to do that? So AIMMS provided distribution functions. So they're including both in the discrete distributions, also continuous distributions. So in the you can see here, also you can find more in AIMMS function reference. We have binomial, geometric, hypergeometric, etc. So those are related to binomial distribution, just based on different type of experiments we're doing. And then for the continuous space, I think most common one is normal distribution, but also there's a beta, beta gamma, the one we use more uniform, for example, so they're in the continuous space. So based on your estimation on the uncertain input, you choose the appropriate distribution to generate the sample. So for our case, we assume that the market price is follow this triangular distribution. So a triangular distribution has a low value and has a high value. So no sample data will fall out of those two values, so always between low and high value. So that's a difference between triangular and the norm. For normal distribution, then there potentially then could go to either direction. But for here, for the market price, we'll use a more practical generation, which is triangular, has absolutely low and absolute high, and then every sample data will generate fall between this range. And there's also a beta. Beta also can be, say, the most likely value. So that's a high density in terms of probability. That's most likely the value will fall into beta. So in order to generate this distribution, then in AIMMS, so the triangular function automatically takes the 3 input arguments. So first you see here, first we have a beta price, which is corresponding to this price, and the price low, and the price high corresponding here. So by calling this statement in AIMMS procedure, if you run this procedure, and the market price, sampled market price will get data falling to this distribution. So this is results. So on the left, we see there is an expected price for different locations here in this couple of cities in here in the US. And on the right, there are sampled price for 1,000 samples for the same locations. And then after we have the uncertain input parameter generated, the next one is to compute the decision outcome under each sample. So the procedures I listed here. So first we want to fix the first stage decision. So if for some decision cannot be changed, we're gonna fix them first, and then we run the model on the sample data, and then so only do recalculate or do reoptimize based for those second stage decisions under the sample data, and then after that we will store results. So the results can all the decision, or make more sense probably the objective functions. So here is the code. We execute those steps. So you see the first line, project start dot nonvar equals to 1. So that's to fix all the project start the first state decision. So once we decide the project will start, that cannot be changed. And then for each sample data, we first assign the sample value, sample market price for this certain sample to the market price, which is the actual data we're using in the model. So by doing this, as you can see, so we don't actually change the optimization model, but instead we kind of put a code outside that by feeding different data to the model. We let the same model run iteratively to get different results. So after we update the market price, we solve the simulation model, and then the next one is to store the result by assign the retrieve the objective function to this parameter, simulated objective for each sample we generated. So that's a loop for simulation. And after we get the results and stored, we want to see some statistical analysis. So certain thing the user interested in are, for the mean value, the median value, standard deviation, and the percentile. In order to do this, AIMMS provides some statistical functions. So we list here. So for example, mean, geometric mean, harmonic mean, root mean square. So those are different ways to calculate the mean value of those sample results. And I'll have median, and I have sample deviation, a population deviation, so the different way to calculate the deviations. Skewness is to measure how symmetric the distribution is, and the kurtosis, that to measure the how sharp the peakness of the peak of the distribution. And then we have correlation and rank correlation, that's different correlation between two random out results. So some example we have here. So on the left we see that are the values we're interested in, for example, mean value, median. On the right are the functions we called, and also list the what is the actual argument we're using here. So for example, they all have same arguments. We'll take the example for mean. First one have the indices, we want to calculate the mean over, and then the next one is which value we want to calculate the mean, which is simulate objective for our sample data, sample results. So we calculate mean, median, max, and mean, and sample deviation. So on the next page, here what we're doing is we want to calculate the percentile. We want to know the 10% and 90% those output. So how to do that? So first we want to sort those value by order. So the original, the sample simulate objective over our sample, they're just by the, it's random, it's not by order, but we can first use this ordered set, which is a sorted order of trials. So that's the ordered set under all the samples. So how to order that is by the value of simulated objective. So use a sort function to order the set. And after the set is ordered, we can take the 10% of the value, which is so we take 100 among all the 1,000 values. Also this one, the 900ths of the 1,000 value as a 10% percentile and the 90% percentile. So let's put together of what we have done so far. So this is a whole run simulation procedure. First, we fix this decision, fix as value as what is currently it is, so optimization won't change the value. And then for each of sample we generated, we first update the parameter we use in the model, and then we run the optimization, and then we take the simulated objective function, and then following we calculate some statistical data we're interested in. And the last thing we're doing here, we want to do some data visualization. This is the graph we want to show to the users. So this is a histogram. Histogram is a graphical representation of the distribution of the value or the observed value. So all the values, they are divided over equal lengths of intervals. So if you see here, this histogram will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 intervals for all the possible values. So all the intervals are equal length. So from this most left, you can think the least value of the objective. The last one is the max value, and then we divide the interval by 10, and then we calculate among all the 1,000 results how many fall into each interval. So as you can see, in this example, those fall into this interval, which has a objective of, so the unit is in million, so 3,044 million results. That's have almost around 200 occurrence happen. So in value fall into this interval. So we know that's most likely scenario. But of course, those natural that have also relative high frequencies as well. So in order to generate this histogram, so AIMMS provide histogram functions, the following. So you can see, again, you can see that in AIMMS function reference. So we just show a piece of code, those functions we used here in order to generate our frequency table. So first, we just create, you can ignore the arguments for now, we just see high level what we have done. So we create a histogram and refer by histogram ID. And after it's created, we set domain. So this function actually will set how many intervals we want for this histogram. So in this case, we'll have 10 intervals. And then for all the results, simulated objective we added to this histogram. So by add observation. And after that, we use the get frequencies function to calculate if for each interval, how many results fall into this interval. And now also get the bounds for each interval to get the left bound and the right bounds. So after that, we just display this histogram frequencies in the AIMMS bar chart in AIMMS WebUI. So this is the results, as we already seen. So far, what we have done is we follow the steps to perform a Monte Carlo simulation. So by doing this, the simulation help us to understand how will the decision we made in the first stage during the MIP solving, how the decision perform under the impact of uncertainty. So then we answer this first question. So the next question is, how will various possible decision plans perform under uncertainty? So by doing this, so what we're going to do is we'll add another outer layer to the simulation we have already done. So before we just do running Monte Carlo simulation for one decision. Now what we're doing is we want to generate multiple decisions first, and then for each decision we run the Monte Carlo simulation, and then in the end we do some additional data visualization. So this is a flow chart. So what we're doing here is first we'll solve MIP model and then get multiple solution by using solution pool. And then the loop here is by retrieve a solution from solution pool. So this loop here is a Monte Carlo simulation we have done. And now we will run this simulation for all the solution in the solution pool. And then we'll finish when we're done. So first we want to generate multiple solutions. There are multiple ways to do so. In this example, we use a MIP solution pool provided by the solver. We're going to see soon how to use the solution pool, how to set it up. But there are also other ways to generate multiple solutions. For example, we can use different initial estimations for the uncertain parameter and generate different initial decision, or we can even use different model to for example, some relation we are not sure about, can model differently to see how to generate initial decision. So there's also, of course, there are other ways to get the initial solution. And after we get the initial solution, then we'll, so first here, let's show how to do the MIP solution pool. So that's some options within AIMMS. So first one, the option we see there is an option to populate. Yes, so that's to tell the solver, yes, we want to generate different, so in the solution pool. And now have set up different options, for example, pool replacement strategy. There are different strategy you can set. Population limit, so we want to generate up to solution pool size number. So that's the number we want to have in the solution pool. And then so there's also some other strategy or option can set here. For example, pool intensity, pool relative objective gap. You can read more for those options again in AIMMS document to see what the different options and which option works best for which circumstance. So after the settings, we're using AIMMS GMP functions to solve the deterministic model. So GMP function basically provide a lower control of the the model, the matrix we're solving, and also we're using GNT function to retrieve the solution from the solution pool in this for loop. So this is for all the solutions we're gonna retrieve from this model to retrieve the solution, and after the solution is retrieved, so because there are multiple solutions, after it's retrieved to this variable, and then we assign to an parameter to record this decision, and which will be used in the Monte Carlo simulation. So, and then after we get this each decision, so this is the first, that's the procedure we just saw in the previous slides, and after we get the decision, and then we're going to run Monte Carlo simulation for each solutions. So this Monte Carlo simulation is the same procedure we saw previously. So this the code so far we saw this accomplish the flowchart we have here, but we want to do one more thing here, is that we want to do distributed computing, because we realize that for the multiple solutions in the solution pool, they're independent with each other. It's possibly we can run them in parallel if we have a powerful computer, or there are multiple different servers can be able to run that, because you can imagine this may take a long time to run. So we want to utilize, if we have the hardware, network resources, we want to be able to utilize that. So how to do that? So in AIMMS Pro, these things it's possible. So what we do is we modify the AIMMS. There are some settings we want to dispatch each session to different AIMMS server, or even the same different session, because server usually has multiple cores. So in order to dispatch that, we use this AIMMS Pro dedicated to server function to dispatch each run to per server. So this, just by calling this, and then there's some callback function, so tell AIMMS what to do after each run is finished. So by doing this procedure, we're able to dispatch different sessions to pro server and then be able to run. So before we run, we just retrieve the solution from the solution pool, assign back for each selected for this current solution, and then based to fix this solution and then run Monte Carlo simulation. So this is the results, and then now I want to show you. So I'm gonna open the UI I already built previously to give a demo how this thing is running. So as you can see, we already tell AIMMS okay to generate 20 solutions from the solution pool, and after that I'm gonna just click the run button. So what it's doing now is to do the master solve and also generate the 20 solutions from the solution pool. So now the master deterministic solve is finished, and then now the AIMMS is running Monte Carlo simulation for each of the solutions. So you can see on the left, I have 3 scenarios running at the same time. That's because I set my AIMMS Pro server to capacity to 3, so which means 3 sessions can run simultaneously. So, but if I go back to my server, see all the jobs currently running, so you can see all the 20 scenarios are dispatched to AIMMS Pro, and 3 are running at the same time, and for those not currently run, they are queued, and then once the current when each scenario is finished, and then the next one will be picked up automatically. So let's do a refresh. So we see they're more finished. Some are still running. So if we go back to the AIMMS interface, so because the setting of this Pro project, so there are additional settings which are not included in this webinar. They're also set up the communication between server and the client, which is my current web session. So make sure that the data is sent back to the client within certain intervals, so I can see constantly. I can see my screen is refreshing. I can monitor the progress. So for those, for example, those results already done. So what we can see here, for each of the solution, we can have a mean value and also standard deviation of this out of the 1,000 simulation we have done. And on the right here, we see the efficient frontier. So on the X is the standard deviation, on the Y is the mean value of the return. And now if we select a certain scenario, for scenario 1, here is a histogram we see similar to we see previously. So for the out of the 1,000 samples of this solution, what is the intervals or frequencies of the certain value. So as we see this one, this scenario 1, the most likely interval is this 2,941 million. So that's relatively low. It's now the highest compared to some of the other decision scenarios we saw. Of course, you can select another scenario to see here. So that's a different scenario. So almost all the waiting for all the scenario. When all the scenarios are done, we will refresh this efficient frontier. So instead of the absolute return, we use a delta between the different scenarios to just really see the differences between scenarios. So if we draw a efficient frontier line for those relatively standard deviation versus mean or risk versus return, let's draw a line somewhat like this, so we can see all those scenarios, those decisions are relatively better than those decisions, so this decision have a relatively lower. So the lower the left, the lower the risk is. So those are relatively has a lower risk versus higher return. So we just see the data visualization. There are some more, of course, we covered how to do basic Monte Carlo simulation in AIMMS, but there are some other topics could possibly helpful for these topics. For example, AIMMS also providing forecasting library, be able to do things like calculate moving average, exponential smoothing, and also some simple linear regression for values. So that's kind of used as a way to do estimation. Now, so there are some question raised also. If we generate sample, we probably should have a way to do the sample infeasibility check. How do we know the sample we generated is actually feasible input, or we can make a decision based on that, give a feasible results. So certain ways, for example, AIMMS provide assertion to evaluate whether input parameters satisfy certain rules. If not satisfied, it probably can regenerate or discard that sample, or can just let the decision run, and then if it is infeasible, discard that sample and regenerate to run another one. All possible ways. There are also, of course, different ways to model adjustable variables. Can make one formulation can provide better result than another. There are also, I mentioned earlier, the data communication between client and pro servers. They're very important in terms of parallel computing, how you assure that there's data storage can be accessed by all the servers or server session, and also some data synchronization between server and client. So Pro also provide functions for that. But for this webinar, we're covering how to do Monte Carlo simulation in AIMMS. So we use AIMMS functions, for example, distribution functions, statistics functions, histogram functions, to provide a means for us to do that. Also, we show ways how to, there's some fixed variables, how to set up a solution pool for multiple decisions. Also, we show on the tool side how to use AIMMS Pro delegate to server functions to set up the server client architect to do distributed computing, and also we show the results in AIMMS WebUI. This is the end of this product webinar. Thank you everybody for attending.